New Zealand is a place far away from the world's major landmasses, where for a very long time, everything that lived there evolved in isolation from the rest of the planet. Tens of millions of years of isolation. Then, by accident, likely carried in with plants or cargo, a new species of praying mantis arrived. In 1978, the South African mantis Mantis cafra was recorded in New Zealand for the first time. After that, it began to spread. A native mantis species was already living there, but the South African mantis turned out to be larger, tougher, and better adapted to local conditions. Its offspring could survive the winter and hatch even in New Zealand's colder southern and mountainous regions. This accidental visitor gained a foothold on the islands, and it liked what it found. But the real problem wasn't just its size or resilience. This foreign species didn't merely move into the native mantis's territory, it brought with it a completely different mating behavior, harsher, more dangerous, and utterly unfamiliar to New Zealand's native mantis. And this is where the story got seriously weird. Let me explain why. Usually when we say an invasive species pushes out a native one, we immediately picture some kind of brutal bullying. The stronger species keep stealing food, territory, and lunch money from the weaker. Eventually, the weaker species just can't keep up anymore. But the poor New Zealand praying mantis wasn't losing in a fight. The male New Zealand mantises started flying to the wrong place. They were supposed to be looking for females of their own species, mating with them and producing offspring. How did that normally work? The female released a chemical signal, the male picked it up and then followed it to find a mate. But now there were South African mantis females nearby, and to the local males, their scent was dangerously tempting. In experiments, males were given a choice: go to a female of their own species or to a female of the invasive species. More often than not, they chose the outsider. So these poor males weren't just randomly ending up in the wrong place, they were genuinely being drawn to the invasive females, because that chemical signal worked like bait. And then it got even worse. For praying mantises, mating doesn't always end romantically. In some species, females can eat the males, sometimes after mating, and sometimes before the males ever get a real chance. It's a way for the female to get extra energy for laying eggs. But things were even worse for New Zealand's local males. They kept flying toward females of another species, wasting time and energy they could have spent finding a real mate. But alas, so the males would fly all the way to a female from another species and try to do what they had come there to do. And then it was over very quickly, because sexual cannibalism was more common among the South African females than among the native species. So instead of mating or even getting a chance to pass on their genes, the local male simply became dinner. It'd be bad enough if it were just one unfortunate male, or two, or even 10 for that matter. But for the species, this became a real reproductive problem, because every one of those males failed to find a female of his own species, left no offspring behind, and disappeared forever, simply because he missed. And the scale of the problem was genuinely alarming. Mating signals in praying mantises can travel over long distances. In other words, a single South African mantis female wasn't just confusing the nearest male sitting on the next leaf over, she could intercept males from a much wider area, and they would all spend time and energy flying toward her, fail to find females of their own species, and then die. And the more often this happened, the harder it hit the native species. Still, it wouldn't be fair to say that confusion over females was the only thing affecting the New Zealand mantis. In nature, things almost never come down to just one cause. Competition, habitat change, and the general pressure of an invasive species may all have played a role. But Mantis cafra is considered one of the species that helped push out the native mantis, and this female trap is thought to be one of the reasons it happened in the first place. The most frustrating part is that for the invasive females, the local male's mistake was actually useful. The better a female was at attracting males from another species, the more food literally flew straight to her. And if those females were more likely to survive and produce offspring, natural selection could gradually favor the ones with the strongest call. So in the end, the native males weren't just disappearing from their own population, they were helping the invasive species thrive at their expense. At this point, the obvious question is, have these invasive mantises totally lost their, can anything be done about them? Maybe we could find something that hunts mantises, because a mantis has always looked almost like the perfect predator. It can sit in ambush, blend into a plant, and wait until its prey gets just a little too close. Then comes the strike. Its front legs snap shut like a trap, the spikes hook into the victim, and there's no getting away. In short, a mantis is a tiny hunting machine. The larger species can even take down more than just insects. They can catch small reptiles, amphibians, and even birds. But nature has a way of keeping every predator in check. And if that check isn't a bigger predator, then it might be something small and completely unexpected. New Zealand already had predatory flies called robber flies, but that didn't mean they immediately solved the South African mantis problem. If the local robber flies had been casually wiping out invasive mantises by the dozen, you wouldn't be watching this video right now. But since Myomantis cafra kept spreading anyway, it was clear that local predators weren't keeping up. That's when researchers began turning their attention to other robber flies, such as Promachus species. Robber flies don't hunt like mantises at all. They're more like flying interceptors. When a robber fly spots an insect, it launches itself at the target midair, grabs on with its powerful legs, and stabs the victim with its rigid proboscis. And the prey doesn't even have to be smaller. These flies have been known to attack wasps, bees, dragonflies, grasshoppers, beetles, butterflies, and other flies. Sometimes they even go after insects that look like serious predators. And suddenly, the mantis doesn't seem so tough anymore. What happens next doesn't even really look like a fight. The robber fly injects its prey with saliva full of toxins and digestive enzymes. That saliva paralyzes the victim and starts liquefying its tissues from the inside. So yes, a mantis can be an excellent hunter. It can snatch flies, cockroaches, and all kinds of other insects, but against an attack like this, even those terrifying front legs don't help much. So it looks like we found the killer that can kill the killer of killers. And this wasn't just some theory about a fly might be able to catch something. In one documented case, a robber fly attacked a European mantis, and the mantis didn't stand a chance. Or was that just the exception to the rule? To find out, they had to imagine what their clash would actually look like. Scenario 1. The robber fly ambushes the praying mantis from behind. In this case, the fly has a solid chance of winning. For the robber fly, it's not about getting into a drawn-out brawl. It's all about landing the first blow. It needs to swoop in, latch on, drive its proboscis home, and inject its venom. After that, it's a waiting game for the toxin to do its job. And evolution has given the robber fly the perfect toolkit for this exact hit-and-run tactic. These flies don't just buzz toward their target like a chaotic ball of wings. They lock onto their trajectory, constantly micro-adjusting their flight to track their prey's movements. Their secret weapon is their eyesight. A robber fly's vision is so razor-sharp that scientists often compare them to elite aerial hunters like dragonflies, even though a dragonfly can be 10 times their size. So if the robber fly spots the mantis and strikes first, the mantis pretty much can only, prey? But there's a catch. The mantis isn't exactly sitting on a branch with a "eat me" sign. It's a master of disguise. If the mantis stays completely still, blending into the foliage, the fly might miss it entirely. It'll just buzz right on by. And that lightning-fast ambush from behind never even happens. Scenario 2. The robber fly attacks from the front. Now this is where things take a turn for the worse. Coming from the front means the fly is heading right into the mantis's line of sight. And if the mantis catches even a glimpse of that movement, it'll strike first. Mantis have an incredibly bizarre and highly precise visual system. In fact, they're believed to be the only invertebrates with 3D vision. It doesn't work exactly like ours, of course, but it's more than enough for hunting. 2 large compound eyes face forward, while 3 smaller simple eyes help them detect changes in light and motion. A mantis can pick up movement from up to 60 feet away. This means that a mantis might ignore a stationary object, but the slightest twitch will instantly grab its attention. So if a robber fly flies straight at it, it automatically becomes a target. Moreover, the mantis doesn't just blindly swipe along a fixed path. Studies show that a mantis can actually adjust its strike depending on how fast its prey is moving. This means even if the fly tries to dodge at the very last second, the mantis can still intercept it. And once those powerful forelegs clamp down on the robber fly, there's absolutely no escaping. Still, that doesn't mean the fly is completely helpless. If the mantis holds its grip too close and the robber fly manages to drive its proboscis in, the showdown could easily end in mutual destruction. Beautiful and dramatic. But there's another factor we can't ignore: the size. If the robber fly goes up against a juvenile mantis, the young mantis stands almost no chance. You can see this clearly in the photo. Next to a tiny mantis, the fly looks like an apex predator that just found an easy meal. A young mantis is simply too small to put up any real fight. It might be quick, it might try to wriggle away, but what's the point? However, the larger the mantis grows, the less room the robber fly has for error. Plus, a mantis isn't exactly soft-bodied, it's covered in an exoskeleton, a built-in suit of armor made of chitin. This chitin provides incredible structural strength without turning the insect into a heavy rock. As a result, the mantis stays light, agile, and capable of absorbing hits, grappling, and surviving ugly collisions. And that armor is actually a huge asset for mantises, because even during mating season, things can turn violent fast. The male and female will try to get the upper hand by grabbing each other with their forelegs. In fact, these legs are so powerful that males sometimes wound females during the struggle, leaving behind marks that look almost like bruises. So they don't just need that armor against enemies, they need it just to survive their own kind. On the flip side, the robber fly has a tool specifically designed to bypass this kind of defense. It's not just a stinger like a bee or a wasp. It's a rigid beak-like proboscis, essentially a heavy-duty piercing tool engineered to puncture tough armor. Even so, size matters. A young mantis is not only easier to overpower, its chitin is also much thinner. Taking on a fully grown adult mantis, however, is a high-stakes gamble where one mistake means death. But it's a gamble the fly can still win. So what we have here isn't your typical predator and prey dynamic. These are two versatile predators. This battle's going to be legendary. And just to prove that the robber fly isn't merely some lucky bug that managed to sneak up on a praying mantis, let me tell you one more thing. Robber flies regularly hunt hornets and paper wasps. Have you ever actually seen one? These aren't soft, defenseless little bugs just minding their own business, entirely helpless to fight back. A hornet is a massive, aggressive predator, sometimes over 2 inches long. Basically, it's an insect the size of your thumb, but with wings, a stinger, venom, and a serious nasty temper. And they aren't just a threat to other insects. People can die from hornet stings too, especially if they're stung multiple times or have a severe allergic reaction, but it's even worse for bees. Hornets will attack honeybee colonies and literally massacre them. Their powerful mandibles are built for exceptionally brutal kills. And yet, robber flies hunt even these guys. Now, this doesn't mean that every single fly is guaranteed to beat every single hornet, but the fact itself is what matters. The robber fly was never just some insignificant weakling next to the mantis. It's a predator fully capable of taking on strong, dangerous, heavily armed insects and winning. Are you wondering what that looks like? Well, scientists have witnessed it, and they took notes. The robber fly lay in ambush, spotted its target, and launched a lightning-fast strike. From there, everything happened mid-air. The fly caught up to its prey, grappled it with its legs, drove in its rigid proboscis, and injected toxic saliva. If the hornet didn't see the ambush coming, you could immediately place your bets on the fly. Because in these fights, the first strike is everything. The hornet could still twitch, buzz, and violently struggle to break free, but it rapidly lost motor control. The toxin did its job. The robber fly didn't need to heroically best its opponent in a fair fight. It just had to hold on tight and wait for the prey to be completely paralyzed. Once that happened, the fly perched on top and started to eat, or rather drink. Hit that like button if you love protein shakes too. However, if the hornet did spot the attack, things got infinitely more dangerous. A hornet isn't just a flying meal ticket, it has powerful mandibles, thick chitin armor, a long stinger, and massive bulk. If the robber fly missed, got a bad grip, or failed to pierce the armor immediately, that quick raid devolved into a dirty brawl. The hornet could spin around midair, catch the fly in its jaws, bite a chunk off, or try to sting it, and against that kind of close-quarters combat, the robber fly doesn't have much in the way of defense. Its entire strategy hinges on landing that first strike. But judging by the fact that robber flies continually manage to catch hornets and wasps, their success is clearly no fluke. Because an insect isn't going to repeatedly attack prey that's guaranteed to destroy it. If it starts a fight, it means it's confident it can win. At this point, you might think we've stumbled onto the perfect solution. If an invasive praying mantis is wrecking the local ecosystem and the robber fly can take down even the toughest insects, the answer's simple, right? We just breed a bunch of robber flies, release them in New Zealand, and let them take care of the South African mantises. I can already picture exactly what that kind of biocontrol program would look like. Somewhere out there, we'd build a massive fly breeding complex. Not a cute little greenhouse with screened windows, but a windowless concrete labyrinth where every single room is kept at a precise temperature and humidity. One room's configured for the eggs, another for the larvae, a third for the adult flies. Because you couldn't just throw robber flies into a box and tell them, now breed. Females lay their eggs on low-lying plants, grass, or in crevices in soil, bark, and wood. That means you'd have to manually build the right surfaces, shelters, warmth, and dim lighting for them. Then the larvae would hatch, and they aren't exactly helpless little worms. Robber fly larvae typically live in the soil, rotting wood, leaf litter, and similar environments. They're also predators, feeding on eggs, larvae, and soft-bodied insects. In other words, a fly factory would instantly turn into a live feed factory. You'd constantly have to haul in other insects, breed them, and ensure the robber flies had enough food at every single stage of life. Because the adults feed on live prey too. If you're looking to release millions of flies every week rather than just 10, you'd need a massive amount of food. First, though, you'd have to catch your first flies. People would have to hike through the wilderness, set up special traps, and hunt for adults. They might even have to use realistic insect decoys to lure the predators in and capture the founders of the future population. From there, it becomes a matter of near military logistics. Once the adult robber flies were ready to release, you could move them into a cold room. The cold makes the flies sluggish. They basically go to sleep, which is exactly what you want for transport. Then you'd load them into a metal crate about the size of a standard washing machine and put them on a plane. I looked into it. Theoretically, you could fit about 2 million flies into a small turboprop plane at one time. The plane would fly over the target area, and a custom rotary dispenser would gradually drop the flies through the fuselage at a set rate so they'd spread out along the flight path instead of falling in one massive living heap. Even here, every detail would have to be accounted for. The dispenser would need to stay refrigerated so the flies wouldn't wake up too early. They need to wake up outside in the warm air, ready to get to work as predators. Of course, there's an easier alternative. A technician could just toss the flies out by hand in small cardboard boxes. But there's a pretty stupid risk with that method. The box might not open on impact. If that happens, the whole batch of flies dies inside, never getting the chance to save anyone or eat a thing. That'd be a real bummer. Actually, this whole concept of factories, airplanes, and millions of flies isn't just some sci-fi theory I cooked up. A system exactly like this already exists. Except instead of robber flies and mantises, it targets the screwworm fly, a notorious agricultural pest. To stop it from marching north, the USDA maintains an invisible barrier right along the Panama-Colombia border. It's invisible because there's no concrete wall. Instead, it's powered by human effort. Every single week, planes drop millions of sterile screwworm flies over the rainforests. Panama has a massive round-the-clock breeding facility to breed them. Inspectors patrol vast territories on motorcycles, boats, and horseback to ensure no new outbreaks take root north of the border. The entire system relies on relentless repetition, week after week, year after year. Because if you make even a tiny mistake, you're right back to square one. So the robber fly scheme isn't a ready-to-go action plan, it's a comparable model. Theoretically, you could launch a similar industrial-scale biocontrol program against invasive mantises. We already know how to turn insects into an airborne biodefense system, but there's one tiny little catch to this beautiful plan. Robber flies don't specialize in mantises alone. They are generalist predators that ambush anything they can overpower. Flies, wasps, bees, beetles, grasshoppers, butterflies, basically anything that fits in their jaws and lets its guard down. This means if you just dump millions of robber flies over New Zealand, every native insect population will take a massive hit. The local mantises we're trying to save would end up right on the menu. Brilliant strategy! To save the mantises, let's release a swarm of bugs that eat mantises. What could possibly go wrong? Yet, science might already have an answer to this problem. The flies released over Panama weren't quite ordinary. The screwworm flies dropped from planes were sterilized, exposed to precisely calibrated doses of radiation. The flies remained healthy, active, and fully capable of courting mates. They just couldn't reproduce. This proves we can alter insect behavior to serve a specific ecological purpose, but could we custom program a robber fly? Could we turn them from indiscriminate aerial assassins into targeted bounty hunters? In theory, yes. First, you'd need to study robber flies in the wild, either in New Zealand or in habitats where similar species hunt mantises. You wouldn't be looking for a magical mantis-exclusive species, because that probably doesn't exist. Instead, you'd look for specific individuals that naturally prefer mantises over other prey. You'd capture those specimens, bring them to the lab, and start breeding them. Inside the facility, you'd raise generations of these flies on a strict diet of invasive mantises. Generation after generation, you'd selectively breed them to hone their instincts, ensuring they recognize and target this specific prey. You could also try making it easier for the flies to spot the invasive mantises, for example, by spraying them with something or using attractants so robber flies are more likely to head toward areas with lots of Myomantis caphra. And of course, you wouldn't just drop the flies anywhere, you'd deploy them strictly in the worst hit zones. Sounds like a solid plan, right? But it will only work if you do all of this consistently over a long period of time. You can't just catch a few aggressive flies, feed them mantises for 3 days, and expect them to turn into an elite anti-invasive task force. It requires intensive selective breeding and constant screening to make sure the robber flies haven't reverted to eating everything in sight. All of this takes an immense amount of time, especially since a robber fly spends years, not days, as a larva. For many species, the larval stage lasts 2 to 3 years before they finally emerge as adults capable of hunting and breeding. Building a population of trained robber flies would take much time. The first real, tangible results won't appear for at least another 10 to 15 years. And the entire time, you'd be footing the bill for the facility, the feeder insects, staff payroll, specialized equipment, field research, aircraft, monitoring, and troubleshooting. We're talking astronomical amounts of money. The USDA screwworm program cost millions of dollars, but it made perfect economic sense. If the screwworm pushed north, the damage to the livestock industry would far outweigh the cost of the barrier. With robber flies and mantises, however, the project is incredibly expensive, painfully slow, highly risky, and offers absolutely no guarantee that the flies will actually stick to the target. So in theory, it looks like an impressive feat of biological engineering. In practice, though, it looks like a plan almost no one would want to pay for. You owe me a like. See you later.